Hello, everyone. My name is Xunli. I'm from Liege University. I'm a postdoc here, and I'm very glad to present some of my work today. The topic of my presentation is proving the motion of a molecular rotor by single molecule force spectroscopy. As we know that due to the size difference, machines at a molecular level can show unprecedented properties compared to machines in a macro level. And inspired by nature, molecular machines have evolved from fundamental biological ones to diverse artificial ones, such as molecular muscles, switches, and motors and rotors. And the design of artificial molecular machines that exhibit controlled mechanical motion and perform the sophisticated tasks is an ultimate pursuit of molecular scale engineering. And the rotor as one of the most profitable molecular machines have attracted much attention, and actually people have already used STM to detect and induce the rotational motion of these rotors. But due to the critical experimental conditions of STM, the information in an unbound condition is still missing. So AFM-based-SMFS as a powerful tool to investigate the inter and intra interactions, molecular interactions in an unbound condition is very suitable here for us to do the experiment. So here our aim is to use AFM-based-SMFS to detect the mechanism of this rotational process. And in our experiment, we use a ruthenium-centered rotor with a 5-arm rotor and tripodal stator, and the stator is modified to facilitate its covalently bunkering and gold substrate through the gold superbond. And on the other side, the one arm of the rotor is linked with a PEG chain for its desorption onto an AFM tip. So along with the extraction of the AFM tip away from the substrate, we can stretch this single molecular rotor. And then we use the molecule with biphenyl as the spacer and bromine as the arm to do the experiment first. And here shows a representative force extension curve. We found that there is a plateau in the middle of the stretching curve. And by measuring the plateau length and plateau force from experiments performed on different days, we are able to build the histograms. And we found that the plateau length of molecule 1 is around 1.6 nanometer, which is at the same level with the theoretical maximum length release of rotating half a turn, 2.1 nanometer for molecule 1. So we attribute the plateau to the relative rotation between rotor and stator. And actually in our experiment, it's not possible or not necessary that every time we do the experiment, we stretch the rotor for a full half a turn. Mostly we just grab the peg and then stretch it through a certain angle. So it is reasonable that the measured plateau length is a little bit shorter than the theoretical maximum length release. And then we measure the plateau force is around 40 picnewton. That means the force needed to rotate this molecule 1, the rotor part is around 40 picnewton. And to prove our hypothesis, we do the same experiment on rotors with different spacers and arms. And we found that for all these molecules, the plateau length is proportional to the length of the spacer. And for molecules with different spacers and arms, they can all rotate against a force of around 50 picnewton. And then to obtain the mechanical work that can generate during this rotational process, we perform the pulling relaxing experiment. And in a typical pulling relaxing experiment, the molecule is stretched and relaxed for several cycles without rupturing. And here shows a package of pulling relaxing experiment occurs in several cycles. And we found that the stretching and relaxing curves follow the same pattern in the same cycle and also in different cycles. So by measuring the area under each plateau, we can get the work performed by the molecule against a pulling force. So here we found that for this molecule, At room temperature, the work from pulling and relaxing curves separately, they fall in the same range. So that means the system is already in an equilibrium region and the molecule rotates faster than the rate of our measurement. So the mechanical work equals to the Gibbs free energy change of the process. So for this molecule with at room temperature, the mechanical work is around 10 to 15 kBT. And all the experiments performed above are at a pulling speed of 200 nanometer per second. Then we decreased the pulling speed to 20 nanometer per second. And surprisingly, we got a totally different pattern stretching curves with many waves in it. Again, we measured the length of each wave and also build a histogram. We found that the length of wave is around 1.7 nanometer for molecule 1, which is almost the same as the Plato length, 1.6 nanometer. So we also attribute the wave to the relative rotation between rotor and stator. So here is the question, why the same rotating pattern corresponds to two different kinds of stretching curves? According to our calculation, the time it takes to rotate one round at room temperature is autonomously is around 0.04 seconds. So when we use relatively higher pulling speed, like 200 nanometer per second, time needed to rotate once under external force is shorter than its autonomous one round rotation time. So the faster stretching rotating motion domains the process and show as plateaus in the curves. And when we use a relatively slower pulling speed, like 20 nanometer per second, the time needed to rotate once by stretching is longer than its original rotation time, allowing several autonomous rotations before reaching the rupture point, corresponding to waves in curves. So in this way, we observe two types of curves due to the different pulling speed. And then we increased the pulling speed to 1000 nanometer per second. And by we noticed that
left.
Okay, thank you. And we noticed that by changing the pulling speed, the Plato force doesn't change. It means the Plato force doesn't have a pulling speed dependency, and it all keeps around 45 picnewton. And for summary, we've successfully used AFM-based-SMFS to detect the motor rotation, and also we find that the signal is proportional to the length of the spacer, and for rotors with different spacers and arms, they rotate against a force of around 50 picnewton. And we also obtain the value of the work performed by the rotor at room temperature. And we also make the statement that the molecule rotates faster than the highest rate of our measurements. And at last, I would like to thank my Professor Anne-Sophie Douy, and all my colleagues, and thank you for your attention.